You ever look at your phone and it just knows who's in a photo? Or see a self-driving car navigate a busy street? It feels like magic, right? Well, it's not. It's actually the result of this incredible journey, this quest to teach computers how to see. And that's what we're going to dive into today.
Yeah, this is the big one, the central question. For the longest time, this was a huge, huge hurdle. And the solution? Well, it came from looking right inside our own heads.
So, meet the hero of our story, the Convolutional Neural Network, or CNN for short. You can pretty much think of it as an artificial brain, but one that's specifically built to understand visual stuff. Pixels, shapes, you name it. This right here, this is the tech that finally gave machines the gift of sight.
And what a journey it's been. We're going to walk through all the major stops on this road trip, from this humble, pioneering idea all the way to the super powerful, super efficient systems we use today. This is basically the roadmap of a technological revolution.
Okay, so let's rewind. Let's go all the way back to the beginning, to the one that started it all. So say hello to LeNet. You know, back in the 90s, its mission was actually super important. It had to read handwritten numbers on bank checks. And you know what? With a pretty simple structure, just a few layers, it worked. It was the proof of concept. LeNet basically laid the groundwork for everything, and I mean everything, that came after. Now, after LeNet, things kind of went quiet for a bit, but then boom, an explosion of progress. The race for more power was officially on, and it was about to change tech as we know it. And the spark that lit that fuse? A network called AlexNet. So in 2012, there was this huge computer vision competition, right? AlexNet didn't just win, it absolutely crushed the competition. No contest. This was the moment, the exact point in time when deep learning went from this quirky academic thing to the absolute powerhouse that defines the industry today. So, what was its secret sauce? Well, AlexNet brought some brand new tricks to the table. It used something called ReLU, which is kind of like a super fast on-off switch that helped the network learn way quicker. And it used dropout, a really clever idea where you randomly turn off parts of the network while it's training. Why? To stop it from just cheating and memorizing the answers. But the biggest lesson, the one everyone took home, was simple. To get more powerful, you've got to go deeper. And oh boy, did people listen. Just a couple of years later, in 2014, this race to go deeper split into two completely different philosophies, two rival camps trying to push the limits. And this slide just lays it out perfectly. In one corner, you have VGGNet. Its strategy? Brute force. Just stack more and more and more layers. I mean, it worked, but wow, was it a power hog. In the other corner, you have GoogLeNet. It asks a better question. Why not go deeper and smarter? It used these brilliant things called Inception modules. Think of them as special tools that let the network look at an image at different scales all at once. It made the whole thing deep, powerful, and way more efficient. But this obsession with going deeper, well, it was leading everyone straight towards a massive roadblock. Turns out, you can't just keep adding layers forever. Eventually, you literally hit a wall. So, what happens? What actually breaks when you just keep stacking layer after layer after layer? This problem has a name you've probably heard, the vanishing gradient problem. The best way to think about it is like a game of telephone. The instructions on how to learn, they have to pass all the way back through every single layer. When you have a really deep network, by the time the message gets to the beginning, it's just a whisper. It's so faint, the first few layers can't hear it. So they just stop learning. The whole training process grinds to a halt. So the whole field was kind of stuck. How do you get past this wall? The answer came in 2015, and honestly, it was just elegant. The breakthrough was called ResNet, and its big idea was something called a residual block. It wasn't about adding more bricks to the wall, it was about designing a whole new kind of architecture. So how on earth did it work? Well, these residual blocks are basically information highways. They're shortcuts. They let the learning signal completely bypass a few layers at a time, giving it a clean, direct path all the way back to the start. The message arrives loud and clear. It was a simple idea, but it was absolutely revolutionary. It completely solved the vanishing gradient problem, and suddenly, we could train networks with hundreds of layers. Okay, so ResNet smashed the depth barrier. And with that problem solved, the whole philosophy started to change. It wasn't just about bigger is better anymore. The new question was, how can we make these things smarter, more balanced? And that brings us to the modern era and to a network that's perfectly named EfficientNet. The core idea here is so intuitive. The best performance doesn't come from just cranking one dial, like depth, all the way to 10. Nope. It comes from finding the perfect proportions, a beautiful balance between all the key parts of the network. And they came up with an actual recipe for it. The creators of EfficientNet figured out this clever formula they called a compound scaling method. So instead of just blindly adding more layers, they would methodically scale everything up in balance. The depth, the width, and the image resolution, all together, all in harmony. And the result? It was incredible. EfficientNet got state-of-the-art accuracy, even better than some of the huge models that came before it. But it did it using way, way less computer power. And that's the real game changer. That's why you can have this amazing AI running right on your phone, not just in some giant data center. You know, there's a quote that just sums this all up so well. It says that the evolution from LeNet to EfficientNet is really a journey of innovation and refinement. And that really is the key takeaway, isn't it? When you step back and look at the big picture, in just a few short decades, we went from teaching a machine to recognize a handwritten number to building systems that can understand the incredibly complex visual world all around us. And they do it with stunning efficiency. So that leaves us with one last really exciting question to think about. We've seen this incredible journey so far, but as AI continues to evolve and get even more powerful, what do you think the next generation of AI vision will be able to see?